Hey, what's up, Logic fans? It's Ash again. Today we're going to hit section 2.2 of the text, Propositional Semantics 2, and we're going to focus on three important semantic properties of propositions. Let's do it. All right, so the three big semantic properties of propositions are logically true, logically contingent, and logically false. Okay, we're going to explain what these mean. Now, every single proposition without question. So here's every single proposition. You pick one proposition out of the collection of all propositions. You pick one out of a hat at random, all right? It is guaranteed to fall into one of these three categories and only one of these three categories. So these categories are mutually exclusive and mutually exhaustive. Every proposition falls into one, and every proposition falls into only one of these categories, okay? So let's talk about these a little bit. You got your logically true propositions. Sometimes we call those tautologies, a term you may have heard before. We've got our logically contingent propositions, okay? Sometimes we just call them contingents. And we've got our logically false propositions. Sometimes we call those contradictions, which you've definitely heard of in the context of the law of non-contradiction, okay? So we've got two tasks before us. One task before us is to understand what each of these mean. Another task is to be able to actually carry out a routine method or technique for determining of any arbitrary proposition which one of these it falls into. So let's jump into that. All right, so let's start with the concept of being logically true, or the notion of a tautology, okay? A proposition is logically true if and only if on every, right? That should even be capitalized, all right? On every assignment under bivalence, it is true, without exception. On every single one, without exception, it is true. Let's look at an example so you can really feel like you understand this. All right, so let's take this sentence as an example, okay? This sentence, A or not A, okay, says show that it's logically true. So I'm telling you that it's logically true here. But we're going to go ahead and prove that right now. Since this sentence has only one propositional constant type involved, it will have 2 to the 1, that is 2 rows in its truth table. That is to say the propositional constant type A can either be true or it can be false, okay? If A is true, then not A is false. If A is false, then not A is true, okay? So now let's evaluate the sentence. True wedge false is true. False wedge true is true. And look at this. Every row on every assignment under bivalence, this assignment, here's an assignment, here's an assignment, okay? It takes the value true on every single one of them. Therefore, A or not A is in fact logically true. A or not A is a tautology, okay? And the basic idea here is that since on every row it takes the value true, this proposition cannot possibly be false. It is guaranteed to be true. Logic alone guarantees it. There's no need to go out into the world and gather data, do empirical research, right? Make arguments, anything like that. Logic alone guarantees that this sentence, this proposition, is in fact true, okay? And so that's the concept of a tautology, or a logically true sentence, okay? Let's look at another example. All right, so let's take a look at this case. Here's a tautology. I'm telling you that it's a tautology. This is logically true. Your task is to prove it. Pause now, give that a try, and I'll give you a hint in a second. All right, hopefully you've had a chance. Here's your hint, okay? Your truth table is going to look like this. You've got 2 propositional constant types, and therefore you're going to have 4 assignments to consider, 4 rows in your truth table, all right? And you're going to start with this one, and you're going to go true, false, true, false, true, true, false, false, okay? Now see if you can complete the demonstration from here. Pause now. All right, it's not too bad, right? So by the truth table for conjunction, the only time it's going to be true is when both conjuncts are true, otherwise it's false. So that's how that's going to go. And now we're going to have this column arrow this column. So for the first case, it's going to be true, arrow, true, which is true. False, arrow, true is also true. False, and again, anytime you have a false antecedent, you have a true conditional. So these are all going to be true in virtue of that. And look at this. On every assignment under bivalence, this proposition takes the value true. Therefore, this proposition is in fact logically true. This is a tautology, and it should make some intuitive sense to you, right? It says provided both F and G are true, F is true. Right? I mean, so it should be matching up with some intuitive notions. Now, sometimes there are tautologies that are really sophisticated, and you can't do that really quick intuitive check because there's just too many moving parts. There's too many logical connectives and too many propositional constant types and instances of them or tokens of them. And so, if you're looking at some really big nasty one, you can always do the truth table to work it out. But in some of these ones, it is nice to see that it is matching up with your intuitive notions. Okay, so this is a pretty cool thing. You can prove that it's a tautology. What would it be like if you had a sentence and it was not a tautology? Let's look at an example like that, something that's not logically true. Well, let's look at this as an example. Okay, just a really easy case. Is A or B? Is that sentence, is that proposition logically true? Well, it's logically true if and only if on every assignment under bivalence it's true. So here's the start for you. See if you can fill it out and understand what's going on in the truth table that tells you that this sentence is not logically true. This sentence is not a tautology. Pause now. All right, well, let's go through it together, right? So this is just the same old, right? Nothing new here, no tricks, okay? We're just moving along here. And these are all 4 possible assignments for this sentence, okay? Because it's got 2 propositional constant types. And just following the truth table for disjunction, we see that it's going to be true here, true here, true here, and false here. And so is it the case that this proposition is true on every possible assignment? No, there's this assignment where it's false, and it only takes the one. So if there's 10,000 of these, okay, and on 9,999 of them it's true, and on the last one it's false, that sentence is not logically true. It has to be true on every assignment, okay? And that's the concept we're working with here. All right, so I think you've got a good idea of both what intuitively logical truth or tautology is supposed to be and how to systematically test for it. Let's move on to the next semantic property of propositions, logically contingent. Okay, so the basic idea here is that a proposition has the property of being logically contingent if and only if both of these conditions hold. It has to be both, okay? It has to be the case that A, on at least one assignment under bivalence, the sentence or the proposition, okay, is true, and, I'll put this in big bold letters, all right, and on at least one assignment under bivalence, the proposition is false, okay? So we just saw an example of this, and I've left it up here. We noticed, is A or B logically true? The answer was no, because it had at least one assignment where the sentence took the value false under bivalence, right? Well, if we just re-inspect this, we see that, look, there's at least one assignment under bivalence according to which this sentence is true, and there's at least one assignment under bivalence according to which the same sentence here is false, namely this one. So it satisfies both of these conditions. Therefore, this sentence here is logically contingent, okay? This is an example of a logically contingent sentence because on at least one assignment it's true and at least one assignment is false. And the basic idea here is that from a purely logical point of view, the sentence in question in this particular example, A or B, okay, the sentence or the proposition in question, it might be true and it might be false. So from a purely logical point of view, you can't really determine its truth value. You can just sort of see from a purely logical point of view conditions under which it's true, and you can see conditions under which it's false. But from a purely logical point of view, you don't know which of those conditions obtain. And so you can't figure out from a purely logical point of view if it's true or false. That means you got to go out in the world and you got to do some exploring and you got to collect some data, you got to make some observations, and you got to make some arguments to try to figure it out, okay? Notice that in the case of a logically true sentence, you don't know which of the assignments holds, but you know that no matter which assignment holds, the sentence is still true, right? So that's kind of an interesting thing. And in this case, you don't know which assignment holds either, but you do know that depending on which assignment holds, the proposition may be true or it may be false. All right. So that's the concept of a logically contingent proposition, and that's how you test for it. You have to build a truth table, and on that truth table there's got to be at least one assignment where it's true and at least one assignment where it's false. It doesn't matter the proportion of trues to falses at all, okay? And what would be an example of a proposition that is not logically contingent? Well, a good example of a proposition that is not logically contingent would be a proposition that is logically true, right? Because on a logically true proposition, this condition will never hold, right? And so the previous examples, like A or not A, for example, of logical truths or tautologies are examples of propositions which are not logically contingent, okay? All right, let's move on to the last concept, which is the concept of a logically false proposition or a contradiction. Okay, so here's our definition. Logically false or a contradiction. A proposition has the property of being logically false or of being a contradiction if and only if on every assignment under bivalence it is false. So let's try an example together, okay, so that we can really understand this definition. Is A and not A, this proposition here, is that logically false? If it is, prove it. Pause now. All right, so here's a hint for you. Okay, here's your truth table. There is one propositional constant. Therefore, there's 2 to the 1 or 2 possible assignments under bivalence. Fill it in from here if you can. All right, so let's go through and do this together. Hopefully you've had a chance, all right? But we've got our one propositional constant, all right? So it can either be true or it can be false. In the event that it's true, this one is false. In the event that A here is false, this proposition is going to be true. And if we combine these two columns, a true and a false is going to yield true, false, by the truth table for conjunction, okay? And if we have a false and a true, that's also going to yield false. So on every assignment under bivalence, this sentence takes the value false, okay? And therefore, this sentence is a logical falsehood, okay? It's logically false. It is also what's known as a contradiction. And this is a really good sort of paradigmatic example of a contradiction, okay? Because it's sort of the form P and not P. So let me get this on the board. So anything of the form P and not P is going to be known as a contradiction. Notice it's sort of saying P is true and P is false. But by the law of non-contradiction, no proposition can be both true and false. Every proposition has at most one truth value, right? So this is a blatant contradiction, and therefore it's desirable, as is indeed the case here, that any such proposition turns out to be false, okay? And that's a really nice feature of our logic, that it should sort of summarily banish and prohibit contradictions from being true. And any logic worth its salt is going to have that feature. And as you can see here, our logic has that feature as well. Okay, I'm going to introduce a couple more advanced ideas in the next video, so look for 2.2b.